Mic test, can you hear?
Yep.
Okay, good. So let's begin. Here is the exercise to save some time. I've already wrote down the solution now. Okay, so let's take a look. This is exercise 10B. I'm going to go through question 4, 9, and 10. So this is question 4. You have two circles, ABCD and ABPQR. They intersect at A and B. Given that ACPCDR and BMDQ, they are straight lines, right? You want to prove that angle BDC is the same as angle BQP. Okay, so where's BDC, where's BQP? It's here and there, right? But you cannot just say angles in the same segment straight away. This is not the case, because we are not having the correct situation. Angles in the same segment requires like this, right? Within one circle, these 4 points are on the circumference. And this angle and the angle are the same. This is not so direct. So what you need to do is to first say that BDC is the same as angle BAC. Can you see that inside the small circle?
Yeah.
This is because of angles in the same segment. So once you have BAC, then you can realize that, oh, this is actually the same as angle BAP, right? Because ACP is a straight line. So angle BAC and BAP must be the same. So now what I've done is, I just say same angle, a bit extra. But why I wanted to do that is because I want you to realize that, oh, angle BAP is now belonging to which circle? It's the big circle, right? Point B and point P is on the circumference. So that means that you can now use angles in the same segment and conclude it's the same as BQP. Angles in same segment. Is that okay?
No.
Yeah, that's it for this part 1. Easy. Now part 2. Angle NPQ and triangle NPQ and NBA are similar. So where is NPQ? It's over here. Then where is NBA? It's over there. Okay, so these two. Every time you see a ribbon shape, like this ribbon shape, probably you need to use vertically opposite angles, right? Which is this one and this one, the X. So that's exactly what I did here. The first one, angle PMQ and BMA, they are equal because of vertically opposite angles, these two, right? Okay. Then that's the first angle. So I am trying to use AA similarity test. If you remember the 3 similarity tests, AA similarity test, and what else? SAS. This is different from the congruency. This S and this S, S1 and S2, they are proportional lengths and one equal angle. And the angle must be included. As well as a SSS. Also in apostrophe, this one is proportional lengths. Okay, every time there's a mention of S when in every time you're trying to prove similar triangles and I mention S, then it means I want proportional length. How do you spell proportional? Proportional. I can't spell. Okay, we are not saying you want exactly equal length, just proportional. But usually these two are not used. Only the AA similarity test will be required. Okay, because all the most of the properties are involving angles. So I'm not saying it will never come up, but these are rarely tested. Usually you just need AA similarity test. Okay, can. Anyways, first angle found. So now we need the second angle. What's the second angle? Angle MPQ. We're trying to show that MPQ is equal to MBA. MPQ here, MBA there. So why are they equal? Because first one, MPQ is actually the same as APQ. They are the same angle, right? Because P, M, and A are on the same straight line. So if you have APQ, then it must be the same as ABQ. Why? Angles in the same segment, because it's in a big circle. Is my audio still connected?
Yep.
Okay, very good. Can. So now you have equal to angle ABQ already. Then finally you realize, oh, ABQ, isn't that just the same as, what is it, MBA? Just chop off the Q, right? You don't need the extra length here. So there we go. We got our angle MBA. So MPQ equals to MBA angle. Okay, so now that we have two angles that are equal, then we can conclude, oh, these two triangles must be similar by AA similarity test. Okay? Good to go?
Yep.
Can I understand? Okay, good. Moving on. Next one, question 9. You got these 5 parallelograms here. Can you see the 5 parallelograms? 1, 2, 3, 4, 5. This top left, top right, bottom left, bottom right, and the huge one.
Yeah.
All of them are parallelograms. Okay. Part 1. State two triangle that is congruent to triangle ABC. ABC is on the left. Congruent must be ADC. Okay.
Yeah.
That's it. Yeah, or CDA. Actually, that's the orientation matter. Okay, I guess it does. It actually should be CDA and not ADC. Sorry. Because of the orientation. Okay.
Yeah.
Then the next one is state the triangle that is congruent to CHQ. So similarly, it will be the one that is the mirror image. So CHQ, then it will become QKC. Going in opposite direction, sort of like anti-clockwise. Okay.
Yeah.
Part 2, okay. But then part 3. Now you don't need to prove for part 1 and part 2, just state. Then for part 3, prove that the area of BPHC is equal to the area of DCQR. BPHC, DCQR, KR. Okay, so this question, right? What they are trying to get you to do is to make use of part 1 and part 2. We already know that this I'll just shade it in black. This black part, these two triangles, they are equal in area. What else? We also know that this blue triangle and that blue triangle, they are equal in area. Then now we want to show that these two parallelograms are equal. So far, what is the only thing that we can do? What is the only shape that we know has equal area? That has equal area.
Equal area. ABC, CDA. No.
Yes. And more importantly, no. I mean, in general, in theory, what shape is that? ABC, CDA.
Triangles.
We only know that they have equal area if they are congruent what? Congruent triangles. We only have theory involving congruent triangles. Right? But here suddenly it's a parallelogram, and then how? We don't have any SSS, SAS, AAS, and RHS. Those rules only apply to triangles. These are parallelograms. Right? Then how do we prove it?
Prove that
Can you see that this is unshaded?
Yeah.
And these two are shaded?
Yeah.
So do you agree with me that the area? Yes, you're saying.
Prove that the triangle APQ is like same as ARQ.
Yes, correct, exactly. Congruent to AQR. The orientation. APQ then AQR. Okay. Yes. Show that they are congruent. So that means that this line will split into two big triangles that have equal area. Then what can you do next? Well, since these two big triangles are equal area and the black one is equal, blue one is equal, you can just minus away the area, right? Then the remaining part should be equal. Cool. Does that make sense?
Okay. Yeah.
Okay. Then now you get the idea already. Now I just show you the presentation. Here, first step is to prove that they are congruent, right? So in triangle APQ and QRA, I go ahead to prove that they are congruent by using, AAS property. Two angles same and one side same. So first angle APQ is equals to angle QRA. Why? Because parallelogram, opposite angles are equal. Okay. Next one, AR is parallel to PQ. This is also because of a parallelogram. And what else? AQ is a straight line. So what shape do you see here that I just highlighted?
Z
shape. Z shape. Then you can use which property?
Alternate
angles. So angle here and here are equal, which is what I've stated here. Angle AQP equals to angle QAR. Here's the reason. Alternate angles AR parallel to PQ. Okay. Now, after you have two angles, it's not enough. We still need S, right? AAS, we need a third, we need two sides that are equal in length. And coincidentally, there's an AQ here, right? Which is a common length. So of course it's equal to itself. AQ equals to itself, right? So we're done. We have two angles at one side. Therefore, we conclude triangle APQ, triangle QRA, they must be congruent by AAS property. Okay? Is it clear?
Yeah.
Clear, good. Okay, then now that we have proven it's congruent, now it's just the presentation part, big minus small. So here is how I presented it. You want BPHC, let me just write down. BPHC to be the same as DCKR. Okay, this part and this part must be equal. Okay, let's see the presentation. BPHC is actually equal to area of the big triangle APQ, the left side one, minus away area of the ABC minus the area of CHQ. Maybe I'll color code it the same as what I did above just now. Or was it black color and blue color, right? Right. So after you subtract away these two areas, you realize that, oh, APQ, because of the congruency we proved just now about QR with triangle QRA, the area must be the same. Area of triangle APQ is the same as area of triangle QRA. Likewise, for the triangle ABC area, you can also replace with CDA. And finally, the area of triangle CHQ is the same as area of triangle QKC. This is from part 1 and part 2, right? Congruent, then they are same area. Is it clear? To go from this step to this step? Can?
Yeah.
Can, okay, good. So basically, big triangle minus black triangle minus blue triangle gives us the remaining part. But big triangle on the left has same area as big triangle on the right. Black triangle area on the left is the same as the one on the right. Likewise for the blue. Left is the same as right. So as a result, this guy, if you look at QRA minus CDA minus QKC areas, you just end up with the parallelogram DCKR. Then proven. That's it. Okay? Is it okay?
Yeah.
Can, okay. Next, part 4. Part 4 is a very common type of question when you want to show something times something equals something times something. Every time you see this format, right, you must think of similar triangles, okay? Similar triangles, because when you have similar triangles, let's say 3, 4, 5, and then you scale it up by 2, so 6, 8, 10. What's the key property here? Key property is 6 over 3 equals to 8 over 4 equals to 10 over 5. Equals to, what is it, 2 over 1. It's a constant 2. Does this make sense? Similar triangles, they will scale proportionally. So the ratio of long over short, long over short, long over short must be a constant. So from here, let's say that we have we focus on 6 over 3 equals 8 over 4. Then that means that you can cross multiply. So you end up with 6 times 4 equals to 8 times 3. Can you see that?
Yeah.
So that's how you can get this format. Something times something on the left, something times something on the right. Just like the 6 times 4 equals 8 times 3. Same idea. Okay, I'm just using numbers so that it's easier to understand, but the actual questions, you don't get to see numbers. You only see letters, okay?
Yeah.
Which is more complicated. Okay, now moving on. So which triangle should you deal with? Should we be looking at that similar? First, you must play around with this quantity here. Just crisscross, you guess and check. HC bring over, or is it AC bring over? And then DC bring over, or QC bring over? So that you can end up with a fraction equals to fraction. Here is, I'll just due to time constraint. Do you want to think a bit first, or should I just review the answer?
I think you can just go ahead and review.
But before that, let me just highlight the quantities. So AC is this length here, HC is this length here, DC is over here, and QC is over here. I think by now it should be obvious which two triangles I'll be looking at.
Yeah.
This one and this one, right? ADC and CHQ. Okay. Go and get your charger soon. Okay.
Or
something.
Yeah, it's charged already. I just forgot to join.
Okay. Yeah, and turn on and stuff. Do it while I'm talking.
Yeah.
Okay, so anyways, AC times HC equals to DC times QC. Let's see how we can prove it. So first thing is to realize DCA and HCQ are similar. Okay, maybe it's better if I just take a screenshot of the diagram so it's easier to visualize. Yeah, like this. Okay, so DCA and HCQ, they are similar triangles. How we can prove it? How to prove it? You can use AA similarity test. Angle DCA is equal to angle HCQ, this one and that one, because of vertically opposite angles. What else we have? We have that ADC is the same as QHC angle. Angle ADC, same as angle QHC. This is because of what shape? Z shape, which is alternate angles. I've done over here. And therefore they are similar triangles. Then since they are similar triangles, we can just write down the fraction. AC over QC equals to DC over HC. And then of course you cross multiply. I think I made a mistake here. This should QC, sorry. QC, HC. And then you will be able to get your final answer. Is this clear?
Yep.
Need to repeat anything?
Nope.
Nope. Okay, good. Moving on. Okay, let's take a look at question 10. Now, this one in a figure, O is the center of the circle, AC is a diameter, and PAQ is a tangent to the circle at point A. Part 1, you want to show that triangle CAP is similar to triangle CBA. So maybe it's better if I just draw the triangle what is it? CAP. I copy and paste the exact same diagram. Then I just draw a dotted line and a point B to remind myself that they are there, but I don't want to focus on it. Then it's similar to CBA. So I follow in the exact same orientation, CBA, right? CAP, CBA, but just a bit smaller. But then you realize that there's a common angle. Do you see a common angle? What's a common angle?
Common angle. BCA.
BCA. Very good. BCA.
BCA and BCA.
Correct. Yes, BCA and PCA. They are equal, right? They are in the exact same position. So that's why they are common. So that's your first angle, right? AA similarity test, you got the first A already. What's the second A? This one need to think a bit. The answer I already reviewed, but let me hide it.
Wait, I actually didn't see.
Okay, then think about it.
The second A.
The second angle. Why did it give you all this information? Diameter, tangent.
90.
Yes, 90 degrees. If this is a diameter, then it means you have a semicircle over here, which means that you have right angle in a semicircle. So over here is a 90 degrees. So CBA, right? So over here 90. Where else is 90?
CAP.
Sorry?
CAP.
CAP. This is what's a rule?
Tangent perpendicular radius.
Very good, exactly. Okay, and that's it. Okay, you solved the question already. Now the rest is just presentation. I'll leave you to read on your own now. Okay, part 1.
Okay. It's not working. It's like...
I'll turn off and on again.
Wow. No, I don't know what's going on. It's like...
I don't know how to help you.
No, it's like, it's weird. It's just like turn off and on and off and on.
Oh, not sure what's going on. Okay.
All right.
Okay, if not, you use paper and pen. I'll send you the file later. You can copy after class. Yeah, right. Ken. Now moving on to part 2. So part 2 is a bit more challenging. Here you see AC square equals CP times CB. Wow, how come suddenly got one square? That's when you have to interpret it as AC times AC, okay? So again, it's the same type of question as I mentioned before. You'll see this type of question all the time. Something times something equals something times something. You need to show similar triangles. And then you use this property that long over short equals to long over short, okay? and then you cross multiply, crisscross until you can get to the correct format. So how? Let's play around with this. How about if we just move the AC over, right? If I just move the AC down and I move the CB over. So I end up with like this. AC over CB equals to CP over AC. Then in this case, we should probably make use of the diagram from here. And I hope by now it's a little bit more obvious. AC is this length.
Yeah.
CP is this length. Then CP is where? Here. Where else? AC is there. Just nice. Just nice. That's why this is part 2. Part 2 linked to part 1. You can make use of the diagram. And then you conclude similar triangle, therefore you can get this fraction, and then you just cross multiply, and then you can get this equation. And that's it to the question. That's it to part 2. Is that okay?
Yeah.
Yeah, so you sort of, it's a bit backwards, I know. Like you start with the conclusion, then you divide, and then you look at the triangle. But the proper reasoning, you have to argue in the opposite direction. You'll also realize this in math at university level. Usually your thought process, you start with the question, then you work backwards until you reach the evidence. Then when you try to write it out, you have to start from the evidence and work towards the conclusion. A bit backwards, the presentation. Is that okay?
Yeah.
Can part 2 is done. I'll leave you to read the solution on your own. I write it nicely, then you can go and read. Part 3, state a triangle that is similar to triangle CAQ. Let's see. Oh, I'll let you in.
Hi.
Hello, mic test. Yeah, I can hear you. Can you hear me?
Yeah.
Okay, good. Yeah, so for part 3, state a triangle that is similar to triangle CAQ. Do you see that there's a sort of mirror image going on here? The left half and the right half.
Yeah.
Yeah, exactly. So CAP was similar to CBA, right? CAP, CBA.
So it's
So
similar
similarly,
CDA.
exactly, CDA. Okay, that's it. Right. So that's the first part done already. It's CDA. Then after that, hence or otherwise prove this one equals to that one. This is actually a little bit more challenging. Can you see why?
CD, CQ. Proof that it's the same what?
So what's the strategy? What's the strategy I've been telling you? When you see
like
some
use fraction.
rewrite it as a fraction, right?
Yeah.
And highlight the correct parts to see which triangle you want to focus on.
Yeah, but this is like
Not a triangle, right?
yeah.
So that's when you need to think a bit more. Why is this part under part 3? Why is this part 3? Means you have to use part 1 and part 2.
Okay. CAP similar to
You look,
CBA.
you compare.
AC square equals, this AC square equals to CD times CQ.
Exactly, yes. Then what's AC? Wait, wait, that's not exactly the same, right? It's okay, so we can substitute the left-hand side with whatever was in part 2, which is AC square equals CP times CB. So AC square equals to CP times CB, which is then equals to CD times CQ. So I don't need the middle part anymore. So AC square equals to CD times CQ, you can rewrite as AC times AC equals CD times CQ. Then what do? Highlight again. AC, CD, CQ. Why is this true? Why should this be true?
Why should this be true?
Yes. What's the trick that I teach you just now? Something times something equals something times something. What do you need to do?
Use triangle.
Crisscross and then use a pair of similar triangles. So which is the pair of triangles you should be looking at?
Crisscross, then wait.
I'll give you a bit more space. Okay. You can draw maybe you can draw the triangle here.
Okay.
But first you must rewrite it as fraction equals fraction from here.
Okay.
Good. Then do you think you can still use this triangle, this pair of similar triangles?
No.
Cannot. So what's missing?
This
came from part 1.
CDA.
Yeah, yes, correct.
Triangle CDA.
And
NCAQ.
Exactly, yes. So can you draw it? Can you draw it in this orientation? Like one big, one small in the exact same.
Okay.
Try. Okay, then label the parts.
C A D C A Q. Wait. Whoops.
Where's the A? Where's the Q?
A Q.
Okay, that makes more sense. Yes.
Yeah.
And then as a result, I think, are you convinced that AC over CQ equals CD over AC?
I mean, yeah.
Right, because the let me see, where's my highlighter? Here over here is the AC over CQ, right? Hypotenuse over hypotenuse, and then CD over AC is where the adjacent is these two, right?
Yeah.
Then that's it.
Okay.
That's why they are equal. Okay. Yeah. So you start with the similar triangle first. You can prove it using A similarity test. Then you form that fraction equals to the fraction. Then from the fraction equal to fraction, you cross multiply, you get AC times AC equal to CD times CQ, which means that AC squared equal to CD times CQ. But you recall from part 2 that AC squared is CP times CB. So you can substitute the AC squared on the left-hand side with CP times CB equals to CD times CQ. And then you have proven the question. I've written it nicely below. You can go and read on your own. I'll leave you to read on your own. Okay. The answer I wrote it out already. Okay. Go and read on your own. Okay, moving on. Next, practice now 5, question 2. Let's see. This is a midpoint theorem question. Question 1 is already in the video. Yeah. So let's take a look. So first one, in triangle ABS, P and Q are the midpoints of AS and BS. O is the center of the semicircle ABS, and angle SOB equals to 90 degrees. Prove that part 1, angle SPT equals to angle OBS. Part 2, TQ is to AB is 1:4 ratio. Let's just deal with part 1 first. Angle SPT equals to angle OBS. Where is SPT? It's over here. Where is OBS? It's over there. Okay, how do we show that they are equal? First thing first, you see midpoint, you quote midpoint theorem. Okay, so for midpoint theorem, what does it say? It says, given whatever was given here, P is midpoint of this length, Q is midpoint of that other length. Then you can conclude 2 things. By midpoint theorem, PQ is parallel to AB, PQ is half of AB. Here and here. Okay? Can?
Yeah.
Good. So now that we, more importantly is, for part 1 is this, the PQ equal half AB is for part 2 later. You see, because there's a half going on, it means it's related to a ratio. Here, when we are looking at angles are equal, parallel will be more important. Why? Because parallel, you have 3 special properties about parallel lines. The 3 special letters, what are they?
Z.
Z, F, and Z, right? Alternate angles, corresponding angles, and interior angles. Okay, this one sum up to, sorry, A plus B equals 180. A bit different from the other two. This is talking about equal angles. Pink equals pink, pink equals pink. Oh, but this interior is a bit special. A and B add up to 180. Okay, so this is very important. This is very, very useful. PQ parallel to AB, we can make a lot of special conclusions. So first thing is angle SPT equals to angle SAB. Makes sense, right? Because corresponding angles, F shape, right? Okay.
Yeah.
Good. Then therefore, what else? Angle SAB equals to angle SAO. That's just because AOB is a straight line. It's a diameter, so it's a straight line, right? Then SAO in this case, do you agree that this is an isosceles triangle, SAO? Can you see that this is an isosceles triangle?
Yeah, radius.
Radius, yes. OA and OS are equal. So since this is 90 degrees, the other angle must also be 90, right? Because 180 minus 90, angles on a straight line. So if you know that this is isosceles triangle and you have a 90 degrees.
45, 90.
Exactly, 45, 90, right? So that means that this angle is 45 degrees. So red angle is equal to this angle by corresponding angles, and it is equal to 45 degrees. Now, all we need to do to show that these two angles are equal is to show that this angle and the right side is also equal to 45 degrees. By symmetry, I hope you can tell. The left half, we use this argument about the corresponding angles and then 45, 90. Of course, we can do the exact same argument for the other triangle, right?
Yeah.
So therefore, we conclude already, this must be 45. I wrote it up in a more long-winded way below. You can go and read on your own, but that's the basic idea. The left half, you can use corresponding angles to show that these two angles are equal. And then once you know this, once you identify this angle, you realize it's actually equal to 45 degrees because 45, 90. And the reason why you can have 45, 90 is because it's an isosceles triangle because of the radius, and you know that this is a 90 degrees. Do the same argument for the other triangle, and you'll get this angle to be 45 as well. Since they are both 45, they must be equal. Okay?
Oh, yeah.
45 degrees. Yeah. So now moving on to part 2. Part 2 is TQ is to AB ratio is 1:4. So let's take a look. Can you see that these two triangles are congruent? STP and STQ?
Okay.
But of course you need to prove it. I tried to write up a proof below. The basic idea here is that SPT and SAO, they are similar, right? Two triangles. If they are similar triangles, if this was already isosceles, then that must mean that SPT is also isosceles, right?
Yeah.
You scale it up and down, it stays isosceles, right? So that means that PT and ST are equal. Agree?
Yeah.
So we can do the same argument for the other two triangles, STQ and SOB. They are similar triangles by AA similarity test. There's a common angle here, then there's these two angles which are equal, corresponding angles, right? F shape. So by AA similarity test, we can show these two triangles are similar. And then finally, we conclude that, since this is an isosceles triangle, STQ is also an isosceles triangle. In particular, ST equals to QT. Okay, but wait a minute. If we know PT equals to ST, QT also equal to ST, that must mean that these two lengths are equal. PT equals to TQ with our intermediary ST. Clear so far? PT equals to TQ? Very good. So now that you know PT equals to TQ, therefore T is a midpoint, right? So do you agree with me that TQ is to PQ, must be 1:2.
Okay.
Yes. TQ to PQ ratio 1:2. So what else? We also know that PQ is half of AB, right? By midpoint theorem. Remember this one?
Yeah.
So we can also write down another ratio, which is instead of writing as a fraction, I just use ratio. PQ is to AB is 1:2, like this. Can you see it?
Yeah.
So using ratios, what you can do is you can just times 2 to this guy. Then you're left with 2:4. And these two are both 2
Same.
units.
Yeah, 1 to
Then
4.
finally 1:4. Exactly. Okay, that's it. I wrote it in a more long-winded way. You can also go and read it on your own. Did I actually? Maybe this one I haven't read yet. Okay. Yeah, I'm just gonna leave it there. Yeah, I'll just leave it as it is. Then you can go and work it out on your own. I only wrote down halfway for part 2. You can fill in the blank on your own if you want to write it more formally. Okay, that is for question 2. Can I move on?
Yeah.
Yes, very good. Let's go. Exercise 10C, question 3. Let's take a look. In the figure, P and B are midpoints of AQ and AC respectively. Given that PB bisects angle APC, so that means that these two angles here and there, APB and BPC, are equal. Prove that the angle PCQ is an isosceles triangle. How? So this one, we need to think of it. We need to make use of midpoint theorem. Okay. So P and B, they are midpoints of AQ and AC respectively. So what's the 2 conclusions you can make? The 2 conclusion is the short one is half of the long one, the base. Right? Can you see the base BP and the base CQ? It's sort of like BP is the base of this small triangle ABP. This base CQ is the base of the big triangle ACQ. Right? The short base is half of the long base. That's what this first part is saying. What else? BP is parallel to CQ. Okay? Can?
Yeah.
Then what I proceed to do next is to prove it's an isosceles triangle. I just show that the base angles are equal. And from this diagram, my goal is to make sure that these 2 angles are equal, and I call it A. I need to show that these 4 angles are angle A. So let me just argue like this. First, I let this angle be A. Then because of the bisecting line PB, that means that this other angle must also be A. So A here. Clear so far?
Yeah.
Okay, good. Then what else do we know? We know from midpoint theorem, P and B are midpoints of AQ and AC, that these 2 lines are parallel. Parallel means we can use what 3 letters? What 3 properties? Or you can think of it as 3 letters. Z. Mic test, can you hear me?
Yeah.
What are the 3 letters?
B, Z, B, C.
B. You mean F? No, I thought it's a F. Yeah.
Yeah.
F,
ZF.
C, F, and C. Okay, so which one would be useful here to show that these 2 are A? Pretend you don't know these are A.
I don't know those are A's.
Pretend you didn't know.
Alternate. B BPC equals to PCQ.
Yes, correct. Alternate angles. So okay,
Alternate.
this one not cross anymore. Tick. And this one?
That one.
What do you know?
You can use. You can. Yeah.
No, I don't know.
No, the corresponding angle.
Yes, correct. Corresponding angles. Can you see the F shape here? The hidden F shape. Then these 2 angles must be equal. Okay, that's it. Okay, then the problem solved already. So we have shown that these 2 angles are equal. This one is by corresponding angles. That these 2 are by alternate angles. So since these two angles are both equal to angle A, they must be the base angles of the triangle PQC. And since they are both equal, PQC must be an isosceles triangle. Okay. I'll leave you to read the solution on your own. Okay. Can? Can? Yeah, that's a rough idea. So next one, question 4. In the triangle ABC, right? E is the midpoint of AC, AD and BE. Where are they? Here and here. They intersect at the point F, which is the midpoint of BE. FC and EH, they intersect at G. right?
Okay.
Now, given that AD is parallel to EH,
EH.
prove that EH is 2 times of FD.
FD. Oh. What the hell?
First,
Oh.
midpoint theorem.
Yeah. Okay.
Look at the first sentence. What's your immediate conclusion?
The first sentence. Here. Like, wait, what do you mean?
Yes,
Wait,
correct,
what do
correct.
you
Yes.
mean by my
Yeah, from the first sentence, E is the midpoint of AC. You can quote midpoint theorem and conclude two things. What are the two things?
Oh, yeah. Here.
Huh? So AE equals to EC, that's only one thing.
Oh, two things.
Yes.
E is the midpoint of AC.
Okay. Actually, no, that's not even the when you draw these two lines, you are telling me AE equals to EC. No.
I mean,
that's the definition of midpoint. Not very insightful. The two conclusions. Do you recall?
Conclusion. What do you mean by that?
Wait, hold on a second. Let me read again. Oh, there's not enough information. Sorry. Right. You cannot quote midpoint theorem. You recall midpoint theorem is saying when you have this setup.
Yeah.
This is a midpoint 1. This is a midpoint number 2.
Oh.
Then you conclude parallel and half or length.
Yeah.
L1, L2. Okay, sorry. I was wrong. There wasn't enough information for you to make a conclusion yet. You need 2 midpoints. Here they only gave you 1. Okay, can. Then that is the only conclusion we can have. AE equals EC. What else can we do?
AD and BE intersect at F. Okay. I don't really know. I don't know
midpoint of BE.
Oh, intersect at F, midpoint of BE.
Midpoint means.
So now
this
you know
length
this. Yeah.
Very good. Must use a different number of strokes. Single,
Yeah.
double. Okay. What else do we know?
FC and EH intersect at G. Yeah. I mean, you know that this equals this.
Vertically opposite. Yes.
And you know that this equals this.
Also vertically opposite.
Then this equals this. I don't know. EH to FD.
What's the conclusion we need? EH equals to 2FD. Do you agree with me that this looks like 2 times FD, then this one is like EH times 1. So it's something times something equals something times something.
Yeah.
So what's the trick? What's the first step? We write as a fraction. Yeah.
Divide by 2 equal FD. Oh, wait.
Okay. So it's half a EH.
Yeah.
So that's what we need. We need the FD to be half a EH. How do you prove that? Let's write it down. Doesn't this look like one half of the conclusion of midpoint theorem?
Yeah.
Yeah, actually, you don't even need midpoint theorem. You can't really use midpoint theorem here. Sorry, you don't know that. Okay, actually, you just my hint for you is BFD and BEH. What's so special about these two triangles?
BFD and BEH are similar.
Similar triangles, right? By AA similarity test. Common angle B, and then these two lines are parallel. So there's a corresponding angles. AA similarity test. Okay, good. So what can you conclude straight away? If it's similar.
It is similar.
over long, like this, right? BF over B equals to short over long. How about FD over HE or EH?
EH.
Do you agree that this is true?
Yeah.
Very good. But what's BF over B?
What is BF over BE? Oh, is half because midpoint theorem. So 1 to 2.
Oh, sorry, this one not midpoint theorem. This one is just midpoint because F is midpoint.
Oh, right, yeah.
Sorry. I think I confused you just now. Midpoint theorem requires a setup where you have a triangle like this, and then you have a point here, let's call it, I don't know, A, and another point there, let's call it B. Then you draw a line connecting A to B. And you must know that on the left side, let's call it yellow, the yellow length, A is the midpoint of the yellow. And then the other side, the blue length, B is the midpoint of the blue length. Then the conclusion is, if I just give it a few more names, AB equals to half of PQ, and AB is parallel to PQ. These are the two conclusions you can make from midpoint theorem. Here, this is not midpoint theorem, it's just because it is midpoint. The definition of midpoint, halfway.
Okay.
Yeah, so therefore half, and then finally you just have to realize it's the same as this, and then you cross multiply and you get to this. Okay, done, part 1. Moving on, part 2, hence show that AF equals to 3FD. Sorry. AF equals 3FD. Again, do you see a certain pattern? Crisscross.
Okay. AF over FD equals 3 over 1.
Okay. That could work, yeah.
So which triangle am I supposed to use? Okay.
You haven't made use of point E.
ADC.
Okay.
And
We haven't made use of which point?
F.
Point F used already. F is midpoint, we conclude it's a half.
Oh, I mean G.
G. Okay, what are you gonna do with G?
I don't know.
Okay, sorry, can I just review? What I'm thinking of is sorry, I shouldn't draw two arrows. E is a midpoint, right?
Yeah.
You haven't made use of E. So you're saying ADC. Yes, very promising. Why? Because it involves AF and involves FD, and that's relevant to the question. So this triangle is good.
Oh, EHC.
With EHC. Very good. Those two are what kind of triangles?
Similar.
Oh, similar triangles. But why is it useful?
Common angle.
Why is it useful? Why is it useful?
Because like it has like F in it and like D in it, and like I don't know what you want me to say.
One more important thing. Here.
Oh, ratio. Wait, what? Midpoint.
So you can form a ratio for similar triangles, right? Fraction equals fraction.
Oh, okay. Yeah.
In particular, you can make use.
AE over AC is 1 over 2.
Wait. Nope. Let me draw the two triangles. It's not AE. AE is not the length of a triangle. This is ACD. This is ECH.
I mean EC equal. EC over AC is
much better.
1 over 2.
1/2. Good. But then you can make use of something that's more relevant, another fraction that's more relevant.
Yeah. Use a Wait, actually,
Find F here.
use AD.
AD, okay.
I
AD
mean,
on the
use
bottom.
EH over AD.
Okay, EH over AD. Can, good. But what is, okay,
then
good.
you know that like EH
Ah.
is like 2 to 1 or whatever.
It's 2 times of
That
FD.
useful.
I think so. Let me
Yeah,
think a bit.
okay. Yeah, you know that EH is like EH to like FD is like
2 FD. Is that what you were saying?
Yeah.
Right. Can substitute EH with 2 FD. But what's
yeah,
AD?
yeah.
Well, what's our goal? We want something involving AF and FD. Right?
Yeah.
We have FD, that's good. We have AD, that's not
AD.
good. We have number, that's good.
AD is FD and AF. Wait. Yeah,
Yes.
I mean no, but
Can.
yeah.
Then you just replace it with a sum, right? AF plus
F.
FD.
All right, then you can cancel the FD.
Cannot. Okay, I ask you a question.
Wait.
2 times 5 over 3 plus 5. Does it mean the 5 cancel? You're left with 2 over 3. Huh? Can cancel? You sure can cancel?
Wait. Oh, okay. Yeah, I guess. Yeah, okay.
Definitely
okay.
cannot cancel, right? So you must remember this. When you have a denominator with a plus sign, you must stress. You must start sweating bullets because this is very difficult. So what you should do instead is to hope that the denominator only has a single term.
Yeah.
If you see a
okay.
plus or minus, wow, very bad. So what's a
Then
better
how?
way, a trick? How about if we flip both sides of the fraction? Can you see that half equals to this fraction? How about if we flip it around? We end up with 2 over 1 equals to AF plus FD over what? 2FD.
2FD.
Very useful
then
because it's 2
4FD
times.
equal AF plus FD. Therefore, 3FD equal to AF. Therefore,
Yes.
I mean,
Done
F
already.
equal 3FD.
Yeah, exactly.
Done.
Okay.
Wow.
So not so easy this question. 3F, just subtract FD on both sides. So 3FD equals to AF. Yeah, it's the same thing. Okay, very good. Moving on. Can I? Okay. Can I you can go and read the fully worked out solution here. Okay, move on. Next, exercise 10C, question 5. Let's see. Now you have a figure. PQ is parallel to SRM and K are the midpoints of QR and PS respectively. Wow, finally you have 2 midpoints. Conclusion immediately. Actually, before that. Yeah, correct. I'll keep that at the back of your mind. Let's continue reading the question first.
Okay.
SM is then produced. SM is produced, extend it, make it so that SM and N are all along the same straight lines. Along the same straight line. It meets the point, meets the line segment PQ produced at N. What does that mean? Means PQ produce, SM produce, they meet together at the point N. Okay? Okay, good. Now, part 1, prove that triangle SRM is congruent to NQM. Ribbon. How to prove congruent? Not similar. Okay, maybe you can quote midpoint theorem first, since that's what we know. What's the 2 conclusions?
Wait, but okay. Like this and this, like K and M is the midpoint, right? But it's not like a triangle.
Oh, you're right.
Unless you like, I don't know.
Extend it, right? Oh yeah, you're right. It's not. You can't quote midpoint theorem directly here. Let me see. Okay. Sorry. Yeah, you cannot. Oh, good point. This is not a triangle. Then it's just a midpoint. No? It's just a midpoint. Then we focus on answering the question. SRM, NQM. How do you show that they are congruent? Let me give you the 4 properties that you need. It's either to show congruent triangles. It's either SSS, SAS, AAS, or RHS. So which of the 4? Look at the triangle. X marks the spot. X gives you what?
Vertically opposite angle.
Vertically opposite angles, right? So these 2 angles are equal. So you got 1 angle. What else?
Okay, I see parallel line, interior angle.
Interior, which one? The C shape, where? Where's the C? Interior angle is a C.
QPS RSB. Wait, actually no. Wait, I mean like.
So these 2 add up to 180. Those 2 add up to 180. That's true. It's a trapezium. Yes. So is that relevant?
No.
More importantly, actually, it's QN and SR that are parallel, right?
Yeah.
Then
alternate angle, SRM and MON.
Yes, so this one and that one are equal by alternate angles. So AA, we have shown that they are similar. Not good enough, we want congruent. So look at the properties. AA.
Midpoint RM is MQ.
Yes, correct, because M is midpoint. So no midpoint theorem, but we can make use of the fact it is midpoint. M is midpoint means that RM equals to MQ, yes. So we have AA, so we satisfy AA as property, and then you can conclude it's congruent. Okay? Let me show you the full reasoning here. Okay? Yeah. Good. Moving on to part 2. Area of triangle PSM equals area of triangle PMN. PSM and PMN.
Okay.
Here, area equal doesn't mean that they must be congruent. You can have equal area despite not being congruent. So I don't know if you recall this from EMAth, but when you have 2 parallel lines like this, then can you see all of these triangles that I'm drawing?
Yeah.
They all have, let's say that their base length is all 2 cm, 2 cm, 2 cm. Then their area will all be equal because half times base times height, half times 2 times height, and the height is over here, common height. So as long as you have, as long as you have a common height and equal base, the area is the same. That's the hint.
What the hell? Okay.
PSM, PMN, get the triangles.
Yeah.
They share the same
length PM.
Wait,
what?
Okay. If this is P, this is M, this is S, this is N.
Same height.
Same height. Yes, correct. Yes. Then what else? Same height. So in order for us to show that they have equal area, all we need to do is to show that they have the same 2. Same what? Same length.
Same base.
Same base. Correct. Yes. In other words, we need to show that SM equals to
MN.
Exactly.
SM equals to MN.
That's our goal. And then we are done already. So the question changes to show that SM equals to MN. Then blah, 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 you'll get area equal area. Okay, so why are they equal?
Similar? No.
Congruent. This is part 2.
I mean, you use the triangle, use part 1, use like the SRM congruent to NQM.
Yes, exactly. Congruent means all the angles equal, all the lengths are equal, right? So of course, SM equals to MN. This is because part 1. Congruent. Okay. Yeah, so there's nothing to show. You just have to quote part 1. Or quote congruent. Congruent triangles have to have the same length. Okay, and then we are done. That's it for part 2. Part 3. Okay, maybe one more to finish up the reason. After you show that SM equal to MN by quoting part 1, you say that congruent triangles have equal length. Therefore, you conclude that the area of this triangle is half times SM times the common height h. But the SM can be substituted with MN as what we have shown. So it becomes half times MN times h, which is then equal to area of triangle PMN. I think I showed the reason here. Yeah, I said let h be the perpendicular height. Okay, so it's half times h times SM, then half times h times NM. This can be substituted because congruent triangles. And half times h times NM is just the area of triangle PMN. This first line was because of area of triangle PSM. They both share a common perpendicular height. Okay, part 2 is done. Okay, move on to part 3. Now, area of triangle, not triangle, PQ, whatever it is, quadrilateral. Area of quadrilateral PQRS equals to 2 times of the area of triangle PMN. How do you show that?
How do you show that? 2 times. Yeah, how?
How? So who is bigger? Is it PQRS or PMN?
PQRS.
Okay. PQRS is bigger. Let me think a bit. Can't remember how I solved it.
Triangle PQM is common area. Maybe like QMN and then PKM is like to prove that it's like congruent. I don't know.
Which QMN and which one?
PKM.
PKM. Oh, they are congruent. Why?
Because they are congruent.
What's the reason?
They have to be congruent.
Oh, is it? Let me see. PS. Are they congruent? What? Wait. Wait, sorry, I don't understand the reason why it's congruent. I don't see how they are congruent. PKM and QMN, right? Why?
Because PQRS, then PMN, then like this is like this common
overlap. Oh, okay,
then,
okay.
Then this one is also congruent to here. So like, okay, wait, okay, I don't know what I'm talking about.
Okay, let's I think it's here's an easier way. Let's label the pieces. Here's a very, very useful technique. Label the pieces A, B, C, D, E. Okay. So region A, B, C, D, E, area A, area B, area C, area D, area E. So PQRS, so what we are trying to show here is that PQRS, which is what? PQI as B, C, D, and E, right? Okay, let me get rid of the highlights. This guy is B, C, D, and E, right?
Mm-hmm.
So we can rewrite it as B plus C plus D plus E is equals to 2 times of open bracket triangle area of triangle PMN, which is A plus B. So I brought it, instead of arguing in terms of overlapping whatever, we just do it in terms of algebra. And I think it's clear that that's the overlapping B, but it's actually 2 times. We need 2 times. Okay, let's simplify this a bit. So we end up with 2A plus 2B. Okay, so what we want to show is B plus C plus D plus E, the area of parallelogram, is 2 times A plus B, which simplifies to 2A plus 2B. But of course, this is exactly the same as IE. Cancel for B on both sides. So C plus D plus E equals to 2A plus 1B, or just B. Okay? But what else you know? A and E are
The same.
the same congruent
So
triangles. So maybe, I don't know if you can, maybe we can just substitute the A with E. So it becomes 2E plus B. Does it make sense? I am simply substituting A with E. Okay?
Okay.
Make
So
sense, huh?
PMS
Okay.
and QMN are congruent. Wait.
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 Let's just continue the algebra first.
Okay.
C plus D plus E, just cancel off one copy of E on both sides. Then you're left with just 1E plus B. Then after you're done with the algebra, you bring it back into the picture and think, what's C plus D? This fella here, right? The area of triangle PSM. What's E plus B? It's the other part. Okay, so they are asking us to prove this is true. How? Do you see what I'm doing?
What?
Do you understand the objective now? We are trying to show this. We started with the question, then we translate into this ABCDE diagram, do a bit of algebra, and then we simplify it down into this. So to answer the original question is equivalent to answering why is C plus D equals to P plus E. I don't know if it's equal or not, yeah. It's just okay, definitely if the question has no mistake, this is true. But you have to prove it. Prove that C plus D equals to E plus B. Want to show. Or want to prove. Maybe it's easier if I do one more step. Replace the E with B. Replace the E with B. Sorry, did I say B? I meant A. Replace the E with A. E back with A.
Okay.
And then this becomes C plus D equals to A plus B. I think this is a little bit nicer.
PMN and P triangle PMN and PMS.
So this is really asking us to prove that area of triangle PMS and PMN are equal. But why are they equal?
PM side, common side.
No. It's a lot simpler. Look at part 2.
Oh.
We already answered the question in part 2, right? Why are they equal? I gave the reason. Half times base times height. But they share the same, different base, but same length base. And they share the same height, perpendicular. Right? Okay. So I think this is worth rewriting. The way that I wrote it was in English. Wow, very long-winded. Let me try again with symbols. Easier. Can? Let me try and rewrite this. Okay, I'll just use the same notation A, B, C, D. Yeah. So what I can do is to say that from part 2, we can conclude that area of triangle PSM, which, okay, I'll just write it down. Area of triangle PSM is equals to area of, what is this, triangle PMN. PSM is what? PSM is C plus D. I just substitute on the left-hand side. PMN is what? PMN is just B plus A. Okay, but what do we know? What else do we know? From part 1, area of triangle SRM is congruent to triangle QMN, so it implies that area of triangle SRM equals to area of triangle NQM. That's very long-winded, so we just use symbols to represent it instead. In other words, E equals to A. i.e. E equals to A. Is that okay? Good. So I can call this equation 1, call this equation 2. Then I can say sub 2 into 1, like simultaneous equations. Right? So I end up with C plus D equals to B plus E. Then after that, I can just do more algebra. Let me just use it over here. C plus D equals to B plus E. So now I can plus E on both sides, which means that I will get C plus D plus E equals to B plus 2E. But wait a minute. Maybe I was doing it a bit backwards. I could have just worked with A, but never mind. I'm just trying to read the working backwards. So I also know that E is A. So again, I can sub equation 2. So I end up with C plus D plus E equals to B plus 2 times E. In this case, it becomes A. Maybe I should highlight the E and highlight the A. Sub 2 here. I leave this E alone, right? It's just algebra. Then after that, I can add a copy of B on both sides. How about if I just plus B here and I plus B here? This simplifies into B plus C plus D plus E equals to 2 copies of B plus 2 copies of A. Then I can factor out the 2. I'm left with A plus B. And then finally, how did we even end up with the 2 bracket A plus B in the first place? Oh, that's what the question wanted, right? This is exactly the same as what the question requested for, area of PQRS. And the 2 times of A plus B is 2 times of area of triangle PMN. Is that okay? Can yeah. So this is a common trick. You label every single small piece of the diagram with A, B, C, D, E, F, G all the way, and then you just substitute with letters so that you can bring it from a geometry world into an algebra world. Then you're just doing simultaneous equations and substitution, which is a way more familiar and easier to work with. Okay? Can Okay, moving on. Next, 10B, question 3, question 7. Okay, now this is not part of the homework already. I finished covering your homework. Now I just want to go through extra question because I think I want to move on already. Okay, exercise 10D. I'll just go through 2 more questions. Then the homework I'll give you. I hope that I can start differentiation. Okay, for question 7, okay, I see how much time I have. I may not go through. Okay, I see how. I'll just go through question 3. Then you can try question 7 on your own. The solution is attached. Because question 7 has 4 parts. 4 parts. The solution is here. You can. Yeah, I don't think I'll have time to go through question 7. I'll just go through question 3. Let's take a look. In the figure, CD is a diameter of the circle. AC and BD are tangents to the circle at C and D respectively. BC and AD intersect at a point P, which lies on the circumference of the circle. So they both happen to intersect. Three different curves are intersecting this point P. The curve of the circle, the straight line, and the other straight line. They all meet at the same point P. Okay. Now prove that CA is parallel to DB. How? To prove parallel lines, it's just the three letters, okay? Must remember the three letters. Not 1, 2, 3, no. It's ZFC. ZFC. ZFC, you can use it when you're given parallel lines, then you conclude the angle is the same, but you can also work backwards. When you have a Z shape and two angles are equal, those two horizontal lines must be parallel. When you have a sort of F shape and these two angles are equal, then these two lines are parallel. If you have a C shape and those two angles add up to 180, these two lines are parallel. So over here, how do you show that these two lines are parallel? Which shape do you see? Very good. C shape, right? And this is what angle and what angle? 90 and 90. Yes. Because this is tangent perpendicular to radius. Diameter is just two radiuses. Diameter is two radiuses. This is a tangent. Clear? Yes. Very good. Yes. Correct reason. Now we can move on. Hence, show that CD square equal to AC times BD. How? It's the same question. Previously, you already see a square, right? You've seen a square question, right? What's the trick? Something times something equals something times something. Very good. Then from there, you link it to a what kind of triangle? Leave it. Draw two triangles that are similar and involves those lines. Yes, not congruent, similar. Then you highlight. Maybe you use a highlighter, CD, BD, AC, CD. Different color. I don't know. I think it will help you if it's different color.
No.
CD, B, AC, and CD. Yeah. Right, those two triangles. Okay. So you just need to show that those two triangles are similar, then you're done. Okay. So let me just draw it out nicely. So what I like to do is I see the first triangle, right? I copy and paste in the exact same orientation. Okay. So C on the left, A on the right, D at the bottom. Okay. Then now I want similar triangle. I know that the other guy, the blue guy that you highlighted. Okay, since you use yellow and blue, I'll just do the same. Just make it a bit bigger, but in the same orientation. Also CAD, then what's the orientation? 90 degrees is at the point C, but the other guy is at point D. So I'll just label a point D here. Then now the question is, should it be B here, C here, or C here, B here?
Wow.
This is parallel already, right? Which two angles are equal? What shape do you see here?
Alternate
angle. So that means that you have this angle equals to this angle. In other words, angle CBD, which is somewhere, is equal to angle ACB, which is the same as ACP. But that's not very relevant. ACP is not an angle inside this diagram, right? So maybe, sorry, wrong. Shouldn't be this
the other way.
The other Z.
CAD.
But
CAD
still
equals to ADB.
But ADB, is it inside the triangle?
BDA. Oh no, it's
also
no.
Not. So maybe Z is not so relevant. Let me think a bit. Did I do something wrong?
Is it a wrong triangle?
Is it the wrong triangle? Okay. When I ask you to highlight, can you help me to erase your highlighter?
Yes. Oh, yeah.
Yeah, okay. What I meant for you to do was to highlight piece by piece. So use small colors, yellow and blue use already. Then I'll just use green, purple, light blue, then brown. Okay, like this. Then highlight piece by piece. So let me just do it. AC is green. BD is purple. CD is light blue. CD again is brown. So you just put it a bit to the side like this. Okay, so those are the lengths we want. We need to involve CD definitely. So I think your choice of the triangle is correct. But then we need to show that the angles are equal. That is the issue. Oh, right. Okay. Let's say that this is angle A here. Then how does that help me? This angle here is 90, right?
Okay.
So what's this angle here?
Wait. Yeah, okay, that angle there is 90. So what's this angle here?
90, A, and what's the remaining?
90 minus A.
90 minus A, okay. Is that useful? Oh, right. There's one more hidden 90 degrees. Sorry, I didn't see the first sentence. CD is a diameter, which means you have a semicircle. Which means you can have what kind of triangle in a semicircle?
I saw.
No. What angle in a semicircle? Sorry, mic test, can you hear me?
90.
90 degrees. Yes, correct. Well done. Good. This is 90. This is a straight line. So that means this other angle is 180 minus 90, which is also 90. Just now we were using Z shape, right? Okay, let's just do the Z. Let me think of okay, I have orange. Z shape. So that means that this angle here is angle A. Okay, actually we could have also concluded that from 90 minus 90 minus A. Since here is 90, this other angle here must be 90 minus A. Okay. Actually, is that even useful to us? Okay, I can make this a little bit less convoluted by removing this part. I don't need it. I just need to show this angle and this angle are equal alternate angles. Z shape. Just need to show this is 90 degrees because it's a diameter. And of course, the other side must be also 90 degrees. And because we have a triangle, 180 minus 90 minus A gives me 90 minus A at this corner. Which means that if I am not mistaken, yes, this angle here was also a 90. Maybe I'll use red color. Right, this angle here is also 90. Tangent perpendicular to radius. Then we can look at this triangle now. There's a 90 at the corner. There's a 90 minus A. What's the angle remaining at the top? Sorry, can you hear me?
A.
A, very good. Yes, good. So that means that we conclude this last angle here must be an A. Very good. Finally, we have our angles that are equal. CAD which is our angle A here, is equal to this other angle A, which is your BCD, right? So BCD must be angle A. And since it's on the top right corner, it must also be on the top right corner. So BCD, then that means my orientation must be B at the bottom, C at the top. Is it clear?
Yeah.
BCD, BCD, angle A, angle A. Yeah, sorry, that was a lot of confusion there. Let me use a different color. I'll use blue and I'll underline this in blue so that you can remember it's related. Okay? Can. So now that, sorry, and 1190. Now that we have drawn the two similar triangles, we can finally conclude this, the fraction, right? Which is AC over CD equals to, let me see again, CD over BD. Technically, it should be DC. But of course, CD and DC, they are the same length. Or DC, BD, same direction. This triangle is similar to that triangle. Conclusion is fraction equals fraction. And then from there, you can cross multiply to get the required solution, required statement. Okay?
Okay.
And yeah, you can go and read the detailed solutions here. What else? Question 7, I'll leave it to you. Now I'm gonna move on to the new topic already. Question 7, I'll see if I have time, then I go through. Otherwise, you can go and read on your own. It's very, very long-winded. Part 4 parts. Today, yes, I will introduce to you the most important topic that you ever learn, ever. Calculus, differentiation, and integration. Okay? Are you ready? Do you watch the videos? I send you. There's a lot. There's a playlist. You know the playlist?
Yeah.
There's quite a few videos I sent you, but this guy, let me just bump it. Here. It's a whole playlist on the entire thing about differentiation.
Okay.
Okay, and this guy. Okay, I'll send you a list of your homework later. Go and watch those. Yeah, but let me try and explain differentiation and integration. Let's begin. Okay, so calculus, differentiation and integration. There are two parts to this differentiation and integration. Those are the two halves. We are going to focus on differentiation first. Then once you master differentiation, you gotta pick it up as fast as you can. Then you have to move on to integration, which is built on top of differentiation. I'll just review the spoilers. Integration is just a reverse of differentiation. So if you don't know your differentiation, you're going to be in trouble when you move on to integration. Are we clear on that?
Yeah.
Okay, now very important. Okay, so now introduction. Previously in primary school, you have learned about arithmetic, plus, minus, times, and divide of the numbers, right? You know how to do that. You can, of course, type it in a calculator. Then you move on to secondary school and you learn about algebra. So for example, a squared plus b squared equals c squared. So one example of a, b, and c is 3, 4, 5. So 3 squared 9 plus 4 squared 16 equals to 5 squared 25. 9 plus 16 equals to 25. This is a relationship between the numbers, right? And you use algebra to help you to describe patterns between the numbers. Does it make sense?
Yeah.
Okay. So now we're gonna think about how we think. So we have been thinking. So the entirety of what you have been learning so far has been just descriptions of patterns between numbers, right? Using algebra as well as a few other things. Now in calculus, what we are doing is we are still doing the same thing. We are describing patterns or finding patterns, but this time it's between equations. So I think you have seen before, right? Like volume of a sphere, a ball, is 4/3 pi r cubed. And then you have curved surface area is equals to 4 pi r squared. Can you see the relationship?
Yeah.
Oh, sorry, the cube. Yeah, what am I doing? Cube here. Can you see that they are very, very, very similar? Can you think of a pattern or spot the difference?
The like 1/3 and then the radius.
The power of the radius, right? Power 2, power 3, right? So there's a sort of relationship between them. What if I told you that you have a specific formula you need to memorize that can link them together? Do you believe me?
Yeah.
Yes, huh? Can you think of a formula before I review?
I don't know, probably something to change the power to like, I mean, something that's like
Change the power. What's
bring
the
down
pattern?
the
How
power or
bring
something. I don't know.
you got to try and self-study differentiation before?
No.
No? Okay, bring down the power. Very good. Here, what do you mean by bring down? What do you think?
Probably something to like, I don't know, like like these are like power one, right? Then probably
The
like
pi
no, I don't know.
pi is power 1, yes, but it's actually just a constant. So if we remove the pi, I just call this f of x, and then this one is f prime of x. The pattern will still remain. What I mean is, if you start off with a f of x equals to 4/3 x cubed, then you have f prime of x, it will be 4x squared. What's the relationship? What is the pattern? Okay, you go and think about it. I will review later. Keep it at the back of your mind. Okay, but you can see the pattern, something is going on. I'll review the answer later. Okay, so finding patterns between equations. Okay, previously it's between numbers, now it's between equations. So there are two patterns that you need to, two descriptions that you need to know of, which is basically number one, the derivatives dy by dx, and number two, the integrals, integral of f of x dx. I know these symbols are alien to you and you've never seen them before, but I will introduce them slowly later. For today, just derivatives. Moving on. So what else? Just now I said that algebra can help you to find and describe patterns between numbers, right? But there are other ways to describe it, which are known as the transcendental functions. Okay, it's just a fancy name. Don't need to go into the details, but basically they are called, they are the exponents, the logarithms, and the trigonometrical functions, which you have already learned. I also wrote down some of its applications as a summary. Okay, trigonometry is just okay. These three are just to describe slightly more complicated patterns and describe slightly more complicated patterns. And these three things I wrote down for you what they do. Trigonometry describes circular motion like a Ferris wheel moving or literal sea waves moving up and down, right? And the right-angled triangle is just a tool to help you to see the circular motion. If you have seen the video link I sent you, have you watched this? The German video. You go and watch later. I'll type it. It will be our homework. Okay, go and see the visualization, circular motion. Then exponents is just like describing the growth rate of a population, for example, bacteria, or in a petri dish. Then let's say if you have an equation like p equals e power t, very unrealistic, but just bear with me for a moment. Then this p would be the population size described by an exponential. If you have different values of t, then it will be different points in time, and the population will change. Usually larger t, then larger population size, right? More time, then you will have more growth. So that's how you can model it. If it's like 2 power t, it will be times 2 times 2 times 2. If it's 2 power t, it will mean that your population size doubles every time the time increases by 1 unit. But of course, if you make t the subject, what happens? you can just bring the e over, so it becomes log p base e, right? Remember your logarithms?
Yeah.
So that means that logarithm is just the time. Logarithm is equivalent, if you want to remember, logarithm is just the time taken in an exponential function. Okay, so exponents give you population size, logarithms gives you the time taken to reach a population size. Okay, in the inverse of exponents. Of course, there's another application of logarithms, which is to help you to make exponents, which are really just repeated multiplication, which is a very, very big number, appear smaller and easier to visualize. More specifically, more precisely, you're linearizing the function. So for example, this is the application of straight line or linear law, right? Y squared equal to 6x. You can take ln on both sides. Then you can split it up into a sum. The power can bring down using logarithm rules. Then you can bring the half over if you want to. Then half times ln x plus half ln 6. Then you can rewrite it as y equal mx plus c. Remember this?
Yeah.
This idea, then once the numbers are smaller, you can fit it on a graph report. Okay, so yeah, that's a summary of everything you have learned so far. Now we are going into new territory, calculus, differentiation, integration, which will help you to find patterns between the equations. So far, you have only been describing patterns between numbers. Now we are changing, we are evolving, we are learning something totally new, patterns between equations. Can
Okay. Yeah.
Okay, moving on. Now, first half of the story, derivatives. This is all introduction. Later, I talk about introduction to integrals as well. Integrals, first pattern you need to identify is rate of change. Rate of change. Let's say that you have this physics example. Let's say that you have this train here that's moving along a track, and assume that you can change the speed. The driver can change the speed of the train anytime he wants. Okay, at 4 points, A, B, C, and D. At A, it's not moving, it's just starting. So it has to start from 0 km per hour or meter per second, and then it starts to accelerate. Accelerate means what? Means your speed is increasing, right? It's not just constant speed straight away from 0 to 100 km per hour straight away. You have to gradually increase, right?
Yeah.
Make sense? Then that's known as acceleration. When you accelerate, you will also have inertia or something. You will jerk inside the train, right? You will if you've taken an MRT ever, when the train starts to move off, you will like feel a force that's pushing against you, right? Okay, that's acceleration. But eventually, once you reach a certain speed, let's say you hit like 20 km per hour already, then you just want to stay at the same constant speed. Then that means that you will start cruising. Okay, stay at the same speed. You are still moving, you're just moving at the same speed. Then after that, when you want to slow down, you have to step on the brake and then you have to decelerate slowly. Eventually, you reach point D with 0 km per hour and you stop. Can understand the story?
Yeah.
So now you can translate that story. Very good. You can translate that story into a graph. Y-axis represents distance traveled since point A. X-axis is the time taken. So the graph looks like this. You accelerate, then you travel at a constant speed. So your distance is still increasing. It's just that it becomes a straight line. And then slowly you press on the brake. So you gradually drop down until you hit 0 and you stop moving. Can understand the story?
Yeah.
And I label all the X and Y, the T and distance, X and Y. I'll just call it X and Y. So now let me ask you let me tell you something. Speed is just the rate of change of distance against time. Do you understand what this means?
Like, no.
Okay, rate of change of distance against timer. Well, okay, what's the formula you know for speed? Speed equals to what?
Distance over time.
Distance over time. But then it's a fraction, right? Fraction, we have a special language to describe it in English. It's called rate, or at least in math English. It's called rate. Okay? So in general, rate of change. You must get used to this phrase, rate of change of distance against time. This is the numerator. Maybe I should label. This is numerator. Then time is the denominator. In calculus or in differentiation, we are interested in generalizing this further. So not just distance against time. It could be, let's say, the volume versus the radius. It could be the surface area against the radius. It could be, let's say you're turning a door. Okay, a door. Then there's a certain angle that it sweeps out. We could measure the angle against time. It doesn't have to be restricted to distance against time. It can be anything against anything. Can you understand this idea?
Yeah.
Okay, so numerator over denominator can be anything. Now, just one more point to take note. I've been talking about speed and distance, but do you know the difference between scalar and vector?
One is wow.
Scalar versus vector?
One has direction, one got no direction, or something like that. Both got magnitude
Exactly.
or something. One got
Correct already.
I don't know.
Yes,
Forget.
both got magnitude. Vector more powerful. Vector has an additional property known as direction. Okay, so over here you can change it from speed and distance. They are scalar quantities, but we will not be dealing with scalars. We'll be dealing with vectors. But don't worry, there's not much of math involved. You just need to understand it conceptually. So instead of saying speed, we'll say velocity. Instead of saying distance, we'll say displacement. Remember displacement and velocity from physics class or anything? Science? No, not today. But a basic idea here is displacement is the shortest straight line distance from a starting point to an ending point.
Okay.
Then distance is a bit different. It's more like cumulative distance. You can walk forward 10 meters and walk backwards 10 meters. The distance will be 20 meters, 10, 10. But the displacement will be 0 meters. Make sense? You start from point A, go to point B, then you go back to point A. So you never left point A. Then your displacement will be 0 meters, although your distance traveled is 20 meters. Make sense? Yes, no?
Say that again.
You start at point A, you travel rightwards by 10 meters to point B. Then you travel back by 10 meters to point A. Your total distance is 20 meters, but your displacement is 0. Very good. Okay, you understand already. Okay. Yes, remember already. Okay. We will be dealing with this fella here in Amex, this displacement. Can
Okay.
just conceptually, not a lot of math. Just need to understand the concept. Go forward, go backward, start at the same point, and at the same point, then the displacement will be 0 meters. Okay, so anyways, let's just continue with the simple example of just scalars first. So can you tell me what's the average speed from B to C? Of course, you know already, it's distance divided by time, right? So from B to C, I hope you can tell that the speed is a constant, right? Because you're cruising. You never step on the brake, you never step on the accelerator. You just keep the accelerator at the same angle, so you just travel at the same constant speed, right? Good. So what's the distance traveled from B to C? You see, you start at 100, you end up with 145. So it must be 145 minus 100. Is it clear?
Okay.
Can, right? Then divide by time taken. You look at the graph, you can tell 30 to 15, 15 to 30. 15. So big minus small, 15. Then you end up with 45 over 15, which is 3 meters per second. Can?
Yeah.
Okay, very good. Now we move on to the next one. Average speed from C to D. This time, a bit funny. You're stepping on the brake, so your speed keeps on changing and changing and changing. It should eventually drop and drop and drop until it reaches 0 meters per second, right?
Yeah.
Your speed. But let's just say that we want to find the average speed from C to D. How would we do that? What we do is we draw this thing known as a secant. You remember what's a secant line? You start with a circle, you put 2 points on the circumference, and you join them together. That's a secant. Okay? So same thing over here. It's not a circle, it's a curve. You can sort of have a circle. Then this will be a secant line. Now we want to find the gradient of the secant line. Does it make sense? Gradient of secant line. It's just y1 minus y2 over x1 minus x2. In this case, 240 minus 145 over 60 minus 30. This is like the distance over time. Still the same idea, right? Is it clear?
Yeah.
Can let me just do a quick calculation. I forgot to calculate this. Divide by 30 and I get around 3.16 meter per second. Okay, this is recurring decimal 6666 all the way. Huh? Okay, that is average speed. Very good. So is that realistic? Is that a good number to help us to tell us about the speed of the train as it's slowing down?
No.
Just one fixed number. Not really, right? It's not very informative. So
Yeah,
what we
no.
want, what we wish is to have a instantaneous speed. Do you know what's the difference between average and instantaneous?
No.
No, okay. If you say yes, then I will be a bit surprised. Okay, so instantaneous speed is basically asking what happens if we zoom in, like let's say at a point P, one specific point in time. And I want to figure out what is the speed that the train is traveling at. How will we do it? How will we calculate the speed? You must be thinking, speed must always be y minus y over x minus x, right?
Yeah.
So you get change in distance over change in time. Then in order to find a single point in time, it's a bit weird. Like if it's a single point in time, you want y minus y over x minus x, where x represents time. But if there is only one single point, then there won't be x1, y1, x2, y2. It's just a single point. How do we do a subtraction like that? X1 minus x2, they will be the same point, is it? Then it becomes x2, y2 minus y2 over x2 minus x2, which is like 0 over 0, right? How?
Yeah.
Doesn't make sense, right?
How?
But here in calculus, what we do is we know that there will be this problem of 0 divided by 0, but we will geometrically assume that it is the tangent line. It is the, sorry, let me lead up to it a bit more slowly.
Yeah. Okay.
So far, we have been looking at average speed, which is gradient of a secant line. But then when it's a single point, we can no longer draw a secant, right? Secant means you need 2 points on a curve drawn on a line. But here only got 1 point. So what we do instead is the next best idea, which is a tangent line. Tangent line.
Okay.
And then instead of finding gradient of the secant, we find the gradient of the tangent. Located at where? Located at this point here, point P of the curve. Can? Not just the yeah, okay, then that's the idea. So let's take a look now. Here we have a point P, the coordinates is 40, y coordinate is 220. So can we find out the gradient of this tangent line? The answer is no, right? So far, with the formulas you've known so far, you cannot, right? But here, after you learn about differentiation, you can find the answer. You don't even need to draw the graph. You can, there's a procedure that will allow you to find the answer to the instantaneous speed, or actually instantaneous velocity, which is the gradient of the tangent line. Can you write this down somewhere? I don't know how. Okay, I write it for you, but please write this down, because none of this you can take notes. You need to memorize everything or understand everything. Can't just memorize, it's too much. You need to understand. There is no cheat sheet for any of the formulas I'll introduce, like in any of the courses. Like geometry, like area of a circle, pi r square, quadratic formula, negative minus b plus minus square root b square minus c all over 2a. They might give it to you, but differentiation, they will never give you the formula, usually. They expect you to know this, especially if you're going into engineering. Anyways, here is the idea. Gradient of a tangent at a point P. Rate of change. This is what we'll be focusing on. And the later you'll see a lot of weird formulas, like techniques of differentiation, what product rule, chain rule, quotient rule, all that. They are all just trying to give you the answer to this question. What is the gradient of the tangent at a point P? So that we can find what's known as the instantaneous speed, or in terms of vector quantity, it will be instantaneous velocity at a specific point. Okay, just remember this story, okay? When you're decelerating, your speed keeps on changing. But at one particular point in time, what is the speed? We are interested in finding the answer to that question. Okay? Okay, moving on. Next one. Integrals. The second half of, if you recall what I mentioned here, we are describing patterns between equations, the first way is derivatives. We look at the gradient of tangent lines at a point to the curve. The second way now is integrals, introduction. So it's not very precise. But the key pattern, key idea you need to remember here is big things can always be broken down into the sum of many small things. Okay? So what do I mean? So let's go back to the example of volume of sphere and curved surface area of sphere. Okay, maybe this is not such a, is this a good pattern? This is a good question. Okay, basically, the pattern here is, there is a, okay, is there a pattern? Yes, there is a pattern. I already talked about it. The basic pattern here is that you can do what's known as differentiate a verb to go from the volume into the area, and then you can go backwards, integrate to go from area back into volume. I know these words don't make sense now. I'll explain it later. Okay, but you need to get used to some of the vocabulary. I'll introduce it more precisely later. A more nicer example would be the following. Let's say that you want to figure out what is the area of a circle. Why is it pi r squared? Integration can help you to find the answer to that question. Okay, assuming that the circumference of a circle is 2 pi r, we assume this is not the answer. This is not the answer. Let's assume that the circumference is 2 pi r first. Okay? From there, we can work out the area of a circle. Let's take a look at this diagram. First, you start off with a very blur circle, circumference 2 pi r, radius r. What we do is we split it up into many what we call concentric circles, like this. They all share the same center. Then we slowly unravel it. How can you imagine? You slowly unravel it like this. Unwrap until eventually it becomes a flat, many flat horizontal lines like this. So what you realize is that if you have a lot of these circles, right, very tightly packed together and very close to each other, eventually these horizontal bars they'll be very close to each other, such that it looks almost as if it's a straight line. Can you see that?
Yeah.
So what shape do you form now? What shape is this? Roughly. What shape is this?
Triangle.
It's a triangle. Yes. So you can imagine if you take a very big circle and you chop it up in very finely like an onion into many small layers, many small rings, you can eventually unroll it into, even though it looks like a very jagged staircase shape, if you increase it to infinity, a lot of these circular strips that are unwrapped into many of these rectangles, this staircase shape will eventually become a very smooth straight line. Can you see that?
Okay.
This is the key idea. This is known as a limit. Okay, I don't talk about it. It's not required for AMAX, but this is the general idea you must understand. You can approximate something by chopping it up very finely into tiny pieces and then adding up a lot of those tiny pieces together, which is what I'm saying over here. A big thing like the area of a circle can be broken down into the sum of many small things, many small rectangles. So now in order to find the area of this circle, we can just find the area of each of these rectangles, add them all together. But to find the total area of all these rectangles, it's really just the area of a triangle, right?
Yeah.
And it's a right angle. What's the area of a triangle? Half times base times height. So it's half times r times 2 pi r. Why is it 2 pi r over here? Because this is the very first outermost circular ring that was unwrapped. Can you see that this, let me highlight it in purple. The bottom rectangle here is the outermost ring, which is this outermost ring, which has a circumference of 2 pi r. Can you see that?
Yeah.
Very good. And why is this radius r? It's because it's the r here. It's just the radius. You use however many layers, that will all add up together to have a length r vertically here. So that means that the area of this triangle is nothing but half times r times 2 pi r. What happens to the half and 2? Cancel. what happens to r times pi times r? Pi r squared. Oh, are you not surprised?
Okay.
So that means that we can reduce the area of a circle by using this procedure, chopping it up very finely into many tiny sizes. And that is the idea behind integration. Okay, integration is just a sophisticated way of doing this procedure. Maybe can I just show you a PowerPoint slide? Give me a second. Let me find the slide first. Okay, and let me share the screen. Here, can you see? Is a slide showing?
Yeah.
Okay, very good. Let me just open this. Okay, so I took this from the internet, but Khalid Azad and Audrey McCormick. Okay, so you take any circle, you can draw as many rings inside the circle as you can. So just zoom in a bit. I mean, speed things up a bit. Okay, many rings. So you can then unroll the rings one by one like this. Okay, then line them up from left to right, outermost to innermost from left to right. But you can always split the circle into more and more rings, and they will become skinnier and skinnier. So at first you can see a staircase shape, right? Like
Yeah.
a staircase here. But then as it gets more and more tiny, skinnier, then this staircase eventually becomes a straight line. Then you get a triangle. Okay. Then the area of these two must be the same. Then the base there must be the radius of the circle. They just orient it a bit differently. And that other side must be the circumference, because it came from the outermost ring, the purple one. Okay, and it's 2 pi r. So area of a triangle, what is it? Half times base times height. So half times r times 2 pi r, which becomes pi r squared. Ta-dang! That's how you get the area of a circle, pi r squared. Okay? Okay, very good. Let me change back to my iPad. No time, no time. Oh no. Oh. Okay, back. Yeah, so that is the idea behind integration. You take things that's very big and chop it up into tiny pieces, add them all together. Oh yeah, by the way, for differentiation, I never explained this in detail, but when we eventually get to 0/0, there is this idea of approximating a tangent line using a secant line. What do I mean? What I mean is, let me just draw it somewhere over here. What I mean is, let's say that we have a simpler curve. Let's say this is y equals x squared plus 3. And then this is a particular point, and I'm interested in finding the gradient of a tangent line at that point. In Emacs, you've done this kind of question before, right? You draw on graph paper, then you draw a tangent line and find the gradient of the graph. By finding the gradient of the tangent line, you plot a point, y1 minus y2 over x1 minus x2. Here we provide to you a specific algorithm, a procedure you must memorize on, so that you can find the gradient without drawing the graph, without drawing it precisely on graph paper. Just have to draw a rough sketch. The basic idea here behind, before you proceed to mindlessly memorize all those formulas, the concept is, let's say that this is a point 1, 1 square plus 3. Okay, or you can use f of x notation, then this will be f of 1, f of 1, which is 1, 1 square plus 3, which is 1, 4. We want to find the gradient of the tangent line. What we can do is we can do the following. We could draw a bunch of secant lines like this. Okay, so It passed through this point and this point. Let's label this as P1. Then let's draw another secant line like this. It passes through this point and this point. Let's call this P2. It's still fixed on the same fixed point 1, f of 1. Then eventually, okay, if I just make my pink color line a bit longer, what you realize is that as the P1 goes to P2 and the P2 goes towards let's say a P3, eventually this point that is moving, right? P1 go to P2 and then go to P3, it will get closer and closer towards the fixed point here. Does it make sense?
Yeah.
Okay, good. Then eventually, once we let this P1, P whatever, reach all the way to be the black color point itself, then we will be able to obtain our instantaneous, what do you call it? Instantaneous velocity. If y here represents the distance, then x here represents the time. And more importantly, geometrically, eventually we will get our tangent line. Can you see the tangent line forming? Maybe if I just extend my pink color line a bit longer. Do you see that eventually these secant lines will eventually turn into the one and only tangent line here? Can you see that? Right?
Okay.
Very good. So that's the so this idea of finding the gradient of a tangent line can be approximated by finding the gradient of all these secant lines. Find the gradient of P1, then find the gradient of P2, then find the gradient of P3. Eventually, what happens is that the numerator and denominator will end up being 0 divided by 0. The denominator is very, very small. But even though it's very, very small and you end up with something so weird like 0 divided by 0, you actually end up with an actual answer. Okay? Yeah, maybe I will demonstrate it to you on another day in an Excel spreadsheet, then you will see what I mean. But for now, let me just introduce a few more things still under differentiation. First one, the notation. Y equals f of x. It can also be written as f with a open bracket 0 close bracket and x. This is the function. This is just a function you know from remainder theorem and factor theorem, right?
Yeah.
Remember? Okay, good. Now I need to introduce some vocabulary. The noun here, derivative. The verb, differentiate. So we start off with a function f of x. Then what we can do is we can differentiate the function. It's just some magical procedure that helps us to find the derivative. So if I differentiate y, I end up with the derivative dy by dx. Another notation is you take the f of x, but you put a single apostrophe, and we usually read this as f prime of x. Okay, maybe I should write this down. dy by dx. I will be saying this many, many times now. This one is f prime of x. Please get used to the names. Okay, this is the derivatives. Another way to write it is f open bracket 1 close bracket, like this on the superscript. Okay, it's in between the f of x. Please take note, this is function notation. We are not doing multiplication. It's not f times x. Okay, you know this. It's not the same as f times x. It's function notation. You can put it the machine analogy. X goes in, then f of x comes out. Right? Okay, then of course we can also continue to differentiate a few more times. So we end up with d2y dx squared, d3y dx squared, dx cubed, and then d4y dx4. Sorry, this should be a 4. Then the prime will just keep on increasing the number. So previously got a single, now got double, triple, then 4. So you can keep on differentiating. This procedure can just keep on going. But what you realize is that it's getting quite troublesome. So we can change the notation into number 1, number 2, number 3, and number 4 to represent how many times we differentiated, the number of times we have differentiated. Okay? And you must have open and close bracket like this. Usually we'll just stick to this notation. Maybe, okay, as well as the second notation. This one, a bit rarer. You will only see this in A levels. Okay? Only the first two is what's required. It's first two. Other notations, you will see it's dfx, y single dot, y double dot, y triple dot. You will see this in engineering. Okay. Not now, not used in AMAX. Can?
Okay.
Okay. Can. That's just notation. Okay. Now let me tell you definition. This is the definition. F prime of x is the limit of f of x plus h minus f of x divided by h, and you take the limit as h goes towards 0. What does that mean? It means nothing to you, right?
Yeah.
Limit doesn't mean anything, so we remove it, and it's not needed in AMAX. You just need to understand it conceptually as if you have a y equal f of x, then f prime of x, the derivative of x. Okay, let me just write it down first. Derivative of f of x, it is two things: the rate of change function or the gradient function. Rate of change I mentioned before, it is of y with respect to x, the numerator and the denominator. Maybe let me just shrink this definition down because it's not so relevant. I need to write some things here. Y is the numerator. X there is the denominator. It can change. It can change. Previously, I've been showing you dy by dx only, but actually you can also have d theta over dt. So this will be like angle, this will be like time. When you open a door, how fast is the door turning? Then we will be interested in how fast the door is turning by taking the angle divided by the time. The angle it makes with the, I don't know, with the some straight line. Okay. WRT means with respect to. Okay, just notation, my short form. And why do I also call this the gradient function? Gradient function. Because you must memorize this now. You don't remember this, please remember this idea. The f prime of x is the gradient of a tangent line at a specific point on the function y equal f of x. Okay, the f of x, of course, can be any function. So let's go back to the example just now where we had x squared plus, also constant, x squared plus 3. Or I call it f of x as well. Y equals f of x equals x squared plus 3. Then the derivative is dy by dx, which is also f prime of x. Now I just do it. The procedure is bring down the whole power minus 1 to get the new. So bring down the whole power, get a 2. Then you copy down the same base x. But then the 2, you need to subtract 1. Okay. Then the 3, there's an invisible x power 0, because anything to the power of 0 is equal to 1, if you remember your exponents. So here we can do the same thing, but because there's a plus, you just copy down plus. You're sort of doing it separately. Battery sold separately, term by term, differentiate separately as well. So you differentiate 3x power 0, leave the 3 alone. Then x power 0, what do? There's a 0. You bring it down, then you minus 1. Here's the mantra need to memorize that I tell my students. Bring down the whole power minus 1 to get the new. So 3 times, open bracket, 0, then times x, the same base, copy and paste the base. It's like one block, you just copy and paste. Then the power becomes the original but minus 1. Bring down the whole power minus 1 to get the new power. Okay? What is 3 times 0?
0.
0. 0 times anything is?
0.
So the whole thing becomes a 0. Interesting. Becomes a 0. So a constant becomes a 0. Think back to the definition that I asked you, the simpler version of the definition I asked you. Gradient function is the gradient of a tangent at a point on the curve. Think about it. Why is y equal to 3? If you think of it separately, not y equals the whole thing, but just y equal to 3. How does the graph look?
Straight line.
It's a horizontal line.
I mean, yeah.
Horizontal, must be more precise. Straight line can be many things. Yeah, horizontal, vertical, or diagonal. So it's a horizontal line. Then can you tell me what's the tangent that you draw at, let's say, this point? The tangent.
Tangent at this point, what?
If it's a
What's the
curve, it's very
tangent?
clear, right? There's a tangent here.
Yeah.
But then if you slowly flatten the curve, let's say I make it the curve a bit more flat like this. A bit more flat like this. And then I start tilting it around like this. So where's the tangent to a fully flat horizontal line?
Is it just the line itself?
It's just the line itself, right? Ah, exactly, it is. Which is a horizontal line. Then read the definition. Gradient of the tangent line, the red color.
0.
What's the gradient? 0, exactly, which is why the answer here is 0. Right or not? Make sense?
Okay.
So conceptually, you can go from 3 to 0 straight away. But if you follow this weird procedure of bring down the O power minus 1 to get the u, you can get a 0 straight away as well. How about this part, x squared? This one need to think a bit. This one must follow the procedure. Just bring down O power minus 1 to get the u. But if I just, since I'm talking about it already, let's say that I introduce another term here. Sorry for the messiness, plus 7x. Okay, then again, I can differentiate term by term. So the plus 7x, don't worry, just differentiate the 7x. If you follow the procedure, what is it? Whenever you have a 7 factor in front, you leave it alone. Okay. Then when you have x, there's an invisible power 1 here. What you can do is you can differentiate the x power 1. You write down a multiplication first. Then you bring down the old power 1. Let me write it in pink. Times the same base x, but you minus 1 to get the new power. So the new power will be what? It will be the original 1, but you minus a 1. Does it make sense? Yes. Power 0. Anything power 0 is?
I mean, anything power 0 is 1.
Is 1. So that means that over here we end up with 7 times 1 times x power 0, which is 7 times 1 times 1, which is just 7. Now let's think about it intuitively. What is y equals to 7x? Like this, right?
Yeah.
What's the tangent line to this guy? Remember?
Still itself.
It's still itself. So let me just draw it like this. Then what's the gradient of itself? Y equal mx plus c.
7.
7. That's why the answer here is 7. It's the gradient of the tangent. In this case, 7x gradient is 7. Make sense?
Yeah.
Very good. Now this one, no choice. There's no intuition behind it. X squared must really follow this weird procedure. Bring down O power minus 1 to get the u. And then this becomes what? 2x power 1 plus 7 plus 0. Okay, can. So now let's say we draw the graph of x squared plus 7x. Sorry, I'm going over time. I am okay. I will not charge you extra. Is this okay? Do you need to rush off?
No, I'm very okay.
Okay, can. Good. So let me just summarize whatever we have found. We start off with x squared plus 7x is x times x plus 7. Then we take dy by dx, which happens to become 2x plus 7, right?
Yeah.
Now let's draw the graph of this fellow. X times x plus 7, 2 roots, right? X and negative 7. So probably something like this. Let's say that where's the midpoint? It must be negative 3.5. Let's say over here negative 1. I want to figure out what's the gradient of a tangent line there. Here's the procedure. When you see that this particular point here is, okay, let's just denote this as y equal f of x equals to x squared plus 7x. And this particular point here must be negative 1 comma f of negative 1. Are you comfortable with this notation, f of negative 1?
Okay.
Right, it's really just, okay, you can work it out if you want. Negative 1 squared plus 7 times negative 1, which is 1 minus 7, negative 6. Okay. So my question is, how do you find gradient of a tangent at a point of the curve? Gradient of a tangent at this particular point on the curve. The point being -1, -6. P -1, -6. Here's how you do it. You start with y, you differentiate, you get this expression. Then after that, you sub x equals to -1. Okay? Here. So what sub into where? Sub into the dy by dx. Okay, I don't label one, just dy by dx is fine. What do you end up with? Dy by dx. Here's the funny notation again. More notation, I'm sorry, you have to learn. Draw a vertical line down like this. Then right at the bottom right corner, x equals -1. This tells the whole world that you have upgraded it from a function. Oh yeah, sorry, I forgot to mention. Why did I mention rate of change function and gradient function? What do you know about functions? They always contain what? Is it just a number?
They always contain what? What do they always contain?
Use a different color.
Mm-hmm.
Not okay, not always, but usually must have. Usually we'll have
What?
x, a variable. They contain a variable. Okay, so a formula. A function is a formula, right? Like 2x plus 5. Like f of x equals to 2x plus 5. Means you feed in an x, you get a corresponding 2 times of that number, but you end plus 5. So if x equals to 2, let's say x equals to 7, then it becomes 2 times 7 plus 5. You have a formula to follow. Does it make sense?
Yeah.
Okay, maybe I don't use f, I use g. So rate of change function, a gradient function, a f prime of x function, or dy by dx function is a function, meaning that it is not just a simple number, it is a function, a formula that you have where you can substitute in an x. Is that clear to you? No?
Yeah.
Clear? Okay, so over here, what's the gradient function? What's the rate of change function? What is the derivative of y? It is
2x minus 7.
2x plus 7.
2x plus 7.
Okay, yes. Plus, I hope my handwriting is clear enough. Okay, then after you sub in x equal -1, right? Why can we sub in? It's because it's a function. So you put the x, put in -1 into the x. You end up with what?
5.
2 times -1 plus 7, which is 5. Okay, good. So that means we have found the gradient of the tangent without drawing anything. You didn't have to draw this. Do you see? This procedure doesn't require drawing a picture.
Yeah.
Wow, that's amazing. That means that your art skills can be as lousy as you want. You don't need to draw anymore, right? Not true. Still need to draw a picture. You still need to identify later on maximum and minimum points. Yeah. So, anyways, just remember, just another a very long-winded reminder. You must remember that calculus is built on top of all the other topics you've learned. You need to go and revise everything. Everything I've taught you. You need to know everything. If not, you will have to keep on going back to I forgot what's a plus b bracket square. What's a plus b power 3? I forgot already. Then you have to go back and do your binomial expansion. Square root x minus square root x plus 2, then bracket square. How to expand this? I forgot. Then you will be in trouble. Okay. Please go back and revise. Yeah. For now, just do with simple examples. Okay, so it's a 5, right? So what else do you know? This is a line. It has a gradient and it has a point. A gradient is also known as a slope. A point, a slope. A point, a slope. What can you find?
Or you can find
You have a
What?
tangent line. Only there was a formula to describe this tangent line, right? Or also known as the equation of a tangent line. Remember your coordinate geometry?
Oh yeah, okay, you can find the equation. Or
Poinsot
Poinsot formula.
Remember? Everything must be remembered. You don't tell me you forget.
Okay.
If not, the lesson is going to be extremely long.
X plus 1, y plus over y plus 6 equals to.
Okay. Y minus
Wait,
away the
what?
y coordinate equals to
Okay.
gradient times x minus the x coordinate. That's how I remember it. So you end up with y plus 6 equals to 5 times x plus 1. If I just bring it over, I end up with y equals to 5x plus 5, then minus 6. 5x minus 1. Okay. So let me just record down what we have. Y equals 5x minus 1. Y equals to x squared plus 7x. And x at x equal to -1, we want to have the tangent line. Just to convince you that this is true, let me use Desmos graphing software. Is that okay? Have you record? Can you? Okay, wait. I just take a screenshot of this and then I send it to you on Telegram so you can reference while I go to Desmos. I just sent you the photo on Telegram. And I also shared screen. Can you see the shared screen?
Yeah.
Can, and this is the function, and we have the derivative which we found to be 2x plus 7. 2x plus 7 is a line that looks like this. Can you see the straight line 2x plus 7?
Yeah.
Now this is not relevant. Just ignore it. Ignore the picture first. Not for Amex. Ignore the picture. What we are more interested in is the tangent line we just found. Let me just change the scale a bit. Let me see, this is -7 to 0. So I want my x-axis to be maybe -8. And this would be, how about +1? Yeah. Can you see the tangent line? The green line is exactly tangential to the point -1, -6.
Yeah.
It only touch 1 point. So this procedure definitely works. Are you convinced?
Yeah. Yeah.
Okay, very magical procedure that unfortunately I'll explain maybe a little bit more of the intuition behind it next lesson. For now, what I want you to take away is there is the main idea. You can find the equation of a tangent line at any point you like on a curve. That's the first takeaway, other than the introduction. And I need you to remember the procedure for differentiation, which is bring down O power -1 to get the limit. Let me write it down formally. I've been purposely not writing it down because I want you to memorize. Can you repeat for me what's the formula?
No.
Differentiation? No. Roughly.
Wait, what do you mean?
Like, how do you go from x squared into 2x?
You bring down the power and then you minus the power by 1. And then yeah.
That's for the first fellow, right? The first fellow.
Yeah.
Then plus 7x. How come it become a 7?
Because x to the power of 0 is 1.
Correct. Yes. When you bring down the 1, then times x power 1 minus 1 is 0. Anything power 0 is 1. Then 7 times 1 times 1 is just 7. The more intuitive way, what's the intuitive way? What's the dy by dx is the derivative, also known as the what function? There are 2 names.
Gradient function.
Gradient function. Yes.
Okay.
And the other name is what?
Rate of change function.
Rate of change function. Okay.
Okay.
But okay, let's look at gradient function. What was the definition?
Oh, damn it.
It provides you with the gradient function gives you the
tangent of
grade.
No,
it gives you the gradient of
the tangent.
The tangent. Where is it?
At the point.
at the point exactly. Okay. Gradient of the tangent at a point. Gradient of a tangent at a point. You better go and memorize this soon.
Gradient of tangent
Gradient of
at a
tangent
point.
at a point. Yes.
Gradient of tangent at a point.
Yes. Gradient of the tangent at a point. Gradient of tangent at a point. Then here, this is the curve. There is a point. You drew a tangent line. You want to find its gradient at this particular point, -1, -6. Right? Can okay, I write down the procedure now. How did we I'm not writing the procedure for finding the equation. I'm writing down the procedure for differentiation. In general, it will be like this. Differentiation technique number 1. I think there's like 5 or 6 techniques. I was actually planning for 4 techniques, but since I'm only talking about the simplest case, I'll update the notes for next week. Okay, basically d by dx. Right, I forgot there was another notation I have to introduce. You put down d by dx, you don't put dy by dx. Then you put down x to the power of whatever. Let's say it's in general n. N is just a number. It's equal to bring down the whole power n times, there's an invisible times here. I don't write the times, it's implied. Then x to the power of n minus 1. I remember it like this. Bring down the old power to multiply -1 to get the new. Bring down the old power -1 to get the new. You must repeat this until you wake up in the middle of the night. Somebody tell you differentiate x power n. Bring down old power -1 to get the new. No hesitation. Can?
Oh my god. Then okay, yeah.
Yeah, you go and repeat it. And what's the definition? What's the 2 versions of the f prime x? What function and what function? Rate of
Rate of change function and gradient function.
definition of gradient function? Find what?
Find that
The name.
gradient of tangent at a point, or find okay.
That's it. Yeah, that's correct. At the point of the function. Take note, of the function, the last part will change. Later on, you'll learn about higher order derivatives like second derivative. What does it mean? Second derivative is really just, well, it's a bit too much for one lesson already, but if you can catch, it's the same as differentiating the dy by dx. Then this guy is the gradient function. Now you try to find the gradient of the tangent line of the gradient function. Does it make sense?
Yeah.
Gradient of the gradient. What does that mean? I'll talk about that's when a gradient doesn't really make sense anymore. You should think of it as rate of change of the gradient function. That is for another lesson. I think that's too much for you to handle.
Yeah.
Rate of change of a gradient. You'll think about it later, not today. But please remember this guy. Okay, and also linearity. Let me just give you the formal name. Linearity of the differential operator. Basically, okay, I give you the full form. I'll use rate. D by dx of x power n plus, let's say, okay, this is an example. Let's say 5x squared. I don't put n, I'll just put a concrete number. Let's say this is 7. This will be 7x power 6. Why? Because we bring down the 7 minus 1 to get the new power. 7 minus 1 is 6. Right? Plus 5. Here, please be careful. Remember when there's a coefficient 5, you leave it alone. Then you times the x squared, right? You take the derivative of x squared. It becomes 2x. 5 times 2 is 10, so 10x. Can? Linearity. Why do I say linearity? Because you can do it term by term. So if I show a bit more steps, what's really going on is the following. We are differentiating x power 7 like this, plus we are differentiating the second guy, 5x squared. Not enough. We can be even more long-winded. Differentiating 5x squared is actually the same as factoring out the 5. Can you see what I just did?
Okay.
You sort of factor out the 5. You can do that if it's a coefficient. Okay, then 5 times differentiate x squared, or rather 5 times the derivative of x squared, which is 2x. There's an invisible times symbol in front. I'll just put it in pink color. You usually don't write it, the pink one. Another example, let's say one more, last one. Let's say we have axn plus b. Oh, I need more space. This would be n, where n is any number, any number. This will be equals to a times d by dx of x power n plus d by dx of b. Does it make sense?
Yeah.
You sort of, it's not exactly the same. Distribute the d by dx, and then when you distribute into a times x power n, the a is a coefficient, you factor it out. So it becomes a times d by dx of x power n plus d by dx of a constant b. Differentiate constant is a 0, by the way. Let me just write it. Can be any constant. It doesn't have to be b. B can be 7, 77, 777, or any negative numbers. Negative pi over e, doesn't matter. It's just a number. Differentiate a constant, you get a 0. Can?
Yeah.
Okay, then I will give you homework involving differentiation and finding equation of a tangent line. Please follow this procedure. That is all for today.
Okay.
I'll send you the file later and homework.
Okay. So I need to revise all the old topics and then do this.
Yes, and the differentiation, this rule. Bring down the O power minus 1 to get the new linearity of the differential operator, finding equation of a tangent line. Later on, we're going to differentiate this procedure to other types of functions, not just x power n. You need to know every single function you have learned so far. Everything can be differentiated. Everything. You find equation of a normal quadratic curve. How about sine curve, cosine curve? Remember?
Wow.
You can also find equation of tangent lines to those. Everything.
Wow.
Exponential curve also can. Logarithm curve also can.
Wow. Yeah. Okay.
Okay, go back and revise. Yeah, and I'll give some basic exercise on differentiation.
Yeah,
this week
I need to
you go and
revise.
yeah, yes. Can. All the best.
Okay. Thank you so much.
Thank you.
Yeah. Thank
All
you
right,
so
bye-bye.
much.
No
Yeah,
worries.
okay. Bye.
Bye. Bye.